of the week 3 instruction. We're almost done, guys, I swear. And today we have the privilege of having Jen give us our little class, giving us our lecture. Very exciting. So on presentation title. And so yeah, I mean, I think this will be really interesting, and this is a lot of stuff that I also want to learn about. So please take it away.
Okay, some of this first logistical thing. So I am muted on my computer.
Oh, right.
Is that correct? Because
That's correct. That is correct. Yeah,
Yeah,
the owl will be on my computer.
So yes, you should be muted. Yeah.
You should be muted with volume off.
And people on Zoom can see my screen. Is that true? Can somebody on Zoom confirm? Yes. Okay.
Sounds like it.
I'm gonna hide the floating meeting controls. Okay. Okay. So hi, I'm Jen, and I am going to talk about some things related to how we parameterize mixing in kind of large scale open ocean environments. I apologize, some of this material is copied from GFD3, so some of you can take that, so it will be a repeat. I apologize, you can leave and I won't be insulted. Okay, so Charlotte, can I?
Yes.
Turn off one of these? Or is that the right one?
Maybe.
I don't know. Oh, that's very dark. Is that any better? Better. Whatever. Charlotte showed this figure, and she said, and you went over this a whole bunch of times in previous lectures, that there's this distribution of energy at lots of different internal waves, lots of different scales in the ocean, and at really large, low frequencies, you have mesoscales, and at some range of frequencies and spatial scales, you have internal waves, and they bounce all around the ocean all the time. And we think they have something to do with turbulence. And so, sorry, I'm very prepared. Okay. So we know, and I actually forget, I looked through Charlotte's lecture this morning, that if you look at the distribution of internal waves in the ocean, so we're specifically thinking about how the whole field of internal waves all bouncing around conspire together to set the patterns of turbulence. And so one piece of that puzzle is that these two fine people, Walter Monk and Chris Garrett, went out and made observations of internal waves in the ocean many moons ago, and they were like, hey, the distribution and the spectra is kind of the same everywhere we go. It kind of, this is a horizontal wave, one horizontal wave number, another horizontal wave number. I think one of these is frequent. No, this is, I don't even remember, frequency wave number. And they said the distribution of energy in all these internal waves, it has a self-similar characteristic everywhere we go in the ocean. So there's the same amount, relative amounts of energy at like larger scales and smaller, medium scales and smaller scales, lower frequencies, medium frequencies, smaller frequencies. And that tends to have a similar shape all over the place, near places where internal tides are made or other sorts of internal waves are made. What's up with that? Like, why is it self-similar everywhere? There must be something happening in the internal wave field that it likes to make itself into the state of self-similarity. It likes to have a certain distribution and not other distributions. So why would that be? Does anybody have a guess?
That's nice, guys, I swear.
Because the limitation on the frequency?
Yeah, so they have to be between F and N. But within that, if you look, here's a spectrum, this just versus frequency here. So they have to be, here's F and here's N, so internal waves, so it like cuts off on both sides. Internal waves have to be within F at the low end and N at the high end. But between those scales, it tends to have a similar distribution. It tends to have this slope in Fourier space. So like the relative amounts of low frequency, medium frequency, high waves all have the same ratio all over the place. So that's kind of weird, right? I don't know. They thought so. They were like, why is this a thing? And so, people, this was in, you know, the 70s or something like that. And so then people spent quite a while trying to figure out what could be happening in the ocean that would make all the internal waves sort of in like a dynamical system sense, try to like resort themselves to the same distribution and spectral slopes over and over and over.
Is it the same reasoning like with surface gravity waves where they may, you know, you might have like thing for wind or like current or longshore ones, but then they eventually end up in groups? And then is that kind of similar to what?
They do end up in groups like surface gravity waves, but there's something else. It is similar to what happens in related to what happens in surface gravity waves. They also have a kind of universal spectral slope. And it's not related to groups, it's related to how they interact with each other for surface waves, which is what we're gonna interlude on the board. Okay. I'm gonna put this up. I'm gonna unplug it. And I'll write some things on the board. So. Okay, so in like waves class or whatever, how many people have seen, all the people that I've taught probably have seen derivation, you know, of basic internal waves, or it was probably in, right, all of you know that. Okay, so you take the momentum equations, you make some assumptions. What assumptions do you make to get normal internal waves?
Small amplitude.
Small amplitude. That's, yeah, so well, let's just go with small amplitude. So if you take the momentum equations and you make a small amplitude assumption, you get a set of linearized equations, which I will not write on the board. But if you plug a solution to them, let's say that you can describe your internal wave by some amplitude u hat times e to the I. It has a horizontal, it has a wave number in the x direction, plus a wave number in the y direction, plus a wave number in the z direction, and a frequency. Right, and so if you plug that type of solution, this is something that is wavy in all three directions and in time. Plug that solution into the linearized equations of motion. What pops out is a dispersion relationship, which tells you, which is a way of encapsulating the physics behind those waves. And that dispersion relationship looks, probably you've seen this before, looks something like this. F squared m squared plus n squared kh squared over where kh squared equals k squared plus l squared. So the horizontal wave number, vertical wave number, and the whole magnitude of the wave number. And you will note, you know, there's a bunch of things where we do this in class that we talk about this with this. One of them is that the frequency only depends on the angle of the internal waves, not the magnitude of the wave number. The limits of this are between f and n. The frequency cannot be smaller than f and cannot be larger than n. But this tells us how that of basically of these 4 parameters, or let's say 3 parameters here, horizontal wave number, vertical wave number, and frequency, only 2 out of 3 are independent. And the relationship between them is governed by this physics. So that's sort of like, so their internal waves governed by this sort of equation that are bouncing all around the ocean, including in your data. And then the next step is to think about what happens if we relax that weak amplitude assumption. So here we have equations of motion that look like this. Du dt equals, you move minus u du dx minus v du dy minus w du dc minus dt dz. That's d and maybe some viscosity terms. So we have things that look like this. And so to derive these internal waves, we said these terms are very small. So, but now what we're going to do, and I'm going to do this in a hand wavy way to not have the whole class be about math. We're going to bring these in an asymptotic way as like the first term and an asymptotic expansion. So we're gonna bring these terms back, but assume that they are small. Smaller than this. So what happens if we bring these terms back and say that we have the solution to these equations mostly looks like internal waves, but to second order, those internal waves might interact, might not be purely linear. They might interact with each other through these terms. So what happens when you do that? You can do this in a more formal asymptotic way, which I will not right now. But let's just think about sort of heuristically what happens when you do that. So let's say we have a whole field of internal waves. They're all bouncing around the ocean. And so in general, our velocity field is going to be it's going to have a whole bunch of waves. It's going to say like we're going to have one wave e to the I k1x plus L1y plus M1z minus omega 1p plus U2 hat e to the I k2x plus L2y plus M2z minus omega 2t plus U3 hat. And there's, whoa. Sorry, no. There's a whole bunch of these waves. So there's a whole bunch of these waves. They're all bouncing around. They all have their own frequencies and wave numbers. And each of them obeys this dispersion equation, but there's a whole bunch of them all bouncing around. So let's look at what happens if I plug in, you can see this is going to get really messy really quickly, but I plug in this infinite series of waves. Yes.
Even though you relax the small amplitude assumption, is it still the same dispersion relationship? Right?
Yes, it's sort of like when you play this type of mathematical game, we say the order, like you do things with little small parameters of epsilons or something. So the order 1 solution is a linear internal wave. And then the next order solution is what happens, like the next order of your small parameter is what happens when you plug your linear wave solution into these terms. Okay.
I have a couple questions. For this dispersion relation, you assume.
I've assumed, that's true. I've assumed n is constant here.
Can you say just one more time why relaxing a small amplitude assumption permits those terms?
Oh, well, I mean, these are just, this is du dt. These are the effective components. And when we derive linear internal waves in the first place, you get the linear internal wave solution by assuming a small amplitude. And so for example, well, this will actually come up in a little bit. So let's think about the size of this term. So the size of this term dimensionally is something like it has a u where u is the velocity associated with the internal wave and has some sort of length scale. This term, so this is term number 2. Let's look at term number 1, has a size which is a u and a time scale. So if we look at the ratio of term 2 over term 1, we get u over L over u over t equals u squared over L times t over u equals u over, I'm gonna write it like that. That's the ratio of this first term to this term. So the length over time in this case is something like a phase speed. So one way to think about the nonlinearity is that it's the ratio between the particle speed of an internal wave, like how fast the water is going, to the phase speed of that wave propagating. And so for linear waves, this ratio is small. But what we'll come back to in a little bit is that for coastal internal waves, right, when waves get big, the particle speed, I mean, why do waves break? We just like all filed out the door and looked at the beach. They all break on the beach because they're going over their handlebars, because the phase speed starts to become comparable, or the particle speed starts to be comparable to the phase speed. So they like, woo, goes over the top and convectively breaks. You could also look at the ratio of this term to other terms, and you get different ways of assessing nonlinearity, but it's I don't know if that was a roundabout answer to your question, Kaylee, but. Okay, so we assumed it was small, but when waves start to have non-infinitely small amplitude, they can start to interact with each other. So, okay, so what happens then if we take our order 0 solution and say each of these terms, so we have a u du dx term, u du dx, just to pick one. There's all of the other ones, vu du dy, all the other, there's like 12 of them or something. We take one of these terms and plug in for u this infinite series of a whole bunch of waves. Then what do we get? All these crazy all the different combinations. And they'll look something like, I'm just gonna write a few for examples. So we would have, u1 hat, u2 hat, e to the I, k, k1 plus k2x plus l1 plus l2y plus omega minus 1 plus omega 2t plus u1 hat u3 hat plus, like, we have all the different combinations, and I've just combined their exponents. Okay, but now, so that is telling us something, but I showed this slide from Charlotte at the beginning and said I was interested in energy transfer. So if I want to think about energy, to get an energy equation out of this equation, what do I do to this to get an energy tendency equation? Yeah, and in particular, so I did not say, but these hatted terms, these are all complex. They include like a phase term in them. These are all potentially complex numbers. So I'm going to multiply this whole thing by u star. Right, and then on the left-hand side, I get u star du dt equals d dt of 1/2 squared. So the left-hand side is one component of the tendency term for kinetic energy. You'd have to do the same with a v squared, etc. And then on the right-hand side, we now have u star u du dx and all of the different combinations, u star v d, I mean, there's going to be a whole lot of combinations. So now what does this look like? If I plug in this product of 3 terms and I plug in my infinite train of waves, what do we get? We get, now we have, each of these are an infinite series, so that, you have all possible combinations. So you get things that look like, u1 star, u2, u3 hat times e to the I, because this one is a star, is a complex conjugate, the sign of the exponent becomes negative, but it looks like something like this. K2 plus K3 minus K1x. I'm going to write all of these to be pedantic. L2 plus L3 minus L1y plus M2 plus M3 minus M1z. It almost doesn't fit. Minus omega 2 plus omega 3 minus omega 1t. So you're going to have an infinite series of these, like, triple products. Does that part make sense? Sort of, at least mathematically. Good.
Yeah, stars as well as just.
No, only that, so. There, one of these is starred and the other two are not, because that's how you get an energy tendency equation. So the U1, in this example, the U1 hat has a star, these two do not, and that's switched the sign, so it's K2 plus K3 minus K1. And then I'm doing this, also there will be a, U1 times U2 star times like all of the combinations. There's really a lot. But without writing out an infinite number of them, what do we notice? This is our tendency equation. So if I wanted to average this in space or time, what do I get if I average over a wavelength in space or time? These are all like oscillatory things, right?
Zero.
It is zero unless what? In what super weird perverted situation would this right-hand side not be equal to zero when averaged? Now we're averaging some sort of average bar. Right, so the only way in some like super weird perverted universe that that the right-hand side would be non-zero when averaged is if okay, so I'm gonna write energy tendency not equals zero if we need K2 plus K3 minus K1 equals zero. Because if this thing goes zero, then it's just, e to the zero is just one. But then it's wavy in this direction too. So we also need and L2 plus L3 minus L1 equals zero, and M2 plus M3 minus M1 equals zero, and omega 2 plus omega 3 minus omega 1 equals zero. So in the super weird situation where all of the wave numbers and all of the frequencies add up together to be zero, if you had that particular combination, then you would have a net energy transfer between these waves. Does that, I mean, that seems highly unlikely, but does that at least make sense mathematically? So, and not only do all four of these criteria have to be true, but they all have to be true while satisfying this dispersion relation still. So what are the chances? And it seems low, right? Because that's a very particular criteria. But the magical thinking behind what we're talking about today is that if you have a broadband field of internal waves with all the frequencies, all the wave numbers, all of the phases, then there will be some cases for which this is satisfied. Right, if you have a continuous distribution, it's like when you do any sort of linear instability analysis, right? It picks out one wave number that actually matches the instability criteria, and that's the thing that grows in any sort of instability analysis. But here, it's if you have a continuous distribution of wave numbers and frequencies, somebody will match this criteria. And then, so you can actually, I'm not going to write it out, you can write out what this net energy tendency term will be if you do all the components, not just the U squared, but the F, dV, dy, and then the potential energy terms. And it is a super long, nasty thing, which has a bunch of constants in there and N's and F's and other things. And you can actually write out, well, maybe I'll just write something. Actually, I'm gonna write okay, yeah, I'm just gonna write one thing so you know what it looks like. What you get is that if you have now I'm gonna write in terms of an amplitude. So now I'm gonna say I have a spectrum, and the spectrum has a whole bunch of different amplitudes. The amplitude of the spectrum at a given wave number is equal to an integral of something called T, which has all of the constants wrapped up in it, any constants, times a bunch of delta functions that represent these criteria. So we have a delta function of omega minus omega prime minus omega prime prime, delta function of k minus k prime minus k prime prime, etc. Times amplitude of k prime, amplitude of k prime prime, minus amplitude of k, this doesn't really matter in detail, times amplitude of k, amplitude of k prime, anyway, there's a bunch of terms here, times dk prime, dk, two intervals. So you can calculate all these terms and you can get a super nasty equation which tells you that the rate of change of any given component of your spectrum is a double integral over all of the wave numbers and frequencies which match these criteria, and it has a term in there that has all of their amplitudes in it. So this is, a piece of work. And these papers from the 70s that derived all this are a joy to read. I will send you a link. There's a whole bunch of them. Like they're okay, so but you do this now. I'm going to switch back to the slides and a couple things. Can I switch back to the slides, or are there questions here?
I do have a question.
Yes.
So I was trying to think of the energy tendency does not equal 0 if those criteria are met.
Yeah.
But I'm trying to think of why it would be 0 if they weren't met, I guess.
So if this is non-zero,
Yeah.
then the energy density is something that is oscillatory. This is an e to the I, whatever. So it's a sine or cosine and z. So if you average over a wavelength, it goes away.
Oh, because of the average. Okay, gotcha.
Because the average.
Yeah. Okay.
So you were trying to look for a net energy transfer. So if you average over wavelengths and frequencies, is there any net energy transfer?
Okay.
Or are they just like momentarily affecting each other and then but it averages, it comes out of the wash? The only way to get a net energy transfer is if this perverted. So this would seem like a crazy, unlikely thing to be describing to you if it didn't turn out to be bizarrely useful. I'm gonna plug back in. So, and I can put, or I'll put in the slides bunch of references, but okay, so then people took that crazy equation and they're like, what if we plug in something that looks like this Garrett-Monk spectrum with this particular distribution? We assume random phases, particular distribution of amplitudes at different wave numbers and frequencies, and yes.
Sorry, Jen, could you share your screen on Zoom?
Yes. It's gonna take a moment to hide the. Okay, so, and it turns out that something that looks like this is a steady state, basically in a steady state with respect to those energy transfers. So in other words, if you take all of those crazy terms and assume you have any type of internal wave field, it tends to shuffle energy amongst itself, given by that equation, until it reaches a shape like this. It likes to be in this shape. And so that was, you know, this is kind of one of these moments of like amazement, like that this universal form of the internal wave spectrum is there everywhere because it self-adjusts through all these weakly nonlinear wave-wave interactions to be in this state. So that's one big take home. That's why it looks like this. The other big take home is that this isn't just, you know, this distribution of internal waves in the ocean isn't just kind of floating on there. There's always internal waves being generated and there's always internal waves breaking. And so the other huge thing, which is the one thing you should remember from today, that all of this crazy wave-wave interaction theory tells us is that there's a net, actually, nope. Okay. That that if you have a spectrum here, now it's just showing one component, and this was a nice paper. I think I saw in Leo's talk, he showed the same picture of Anne Gargett, who is my hero. But so she wrote this paper, anyway, sort of compiling a bunch of spectra of internal waves, and if you plug in all this wave-wave interaction theory, if there's energy being created at low frequencies and low wave numbers, like by an internal tide, something like that. So there's energy coming into the spectrum. All of these wave-wave interactions not only make the shape a universal shape, but they also steadily move energy down to smaller and smaller scales. So they're all bouncing around and weakly nonlinearly exchanging energy with each other. And that makes a general tendency of energy to move from large scales down to small scales. And so the point of this class is supposed to be, so people said, oh, if we know that equation on the board and we know something about how internal waves exchange energy with each other, we could just make measurements of internal waves at the internal wave scales, because microstructure, as you've all learned this past week, is like finicky and a pain in the ass and hard to process and all these things. It's wonderful, but it is challenging. So if you could make measurements of the internal wave field, which you can do from an ADCP or a CTD or, you know, an Argo float or anything that's relatively easier to use, you can be like, I see an internal wave field that has about these properties and this energy level. I can plug my observations into that formula, and that will tell me the rate at which energy through this internal wave field is moving from large scales to small scales. And that is then the same rate at which energy is being dissipated at the small scale end of things. Let's see, I have some examples. Okay. I have some intuition building examples, which I will come back to if there's time. So people proposed these solutions and went out and made a bunch of measurements of turbulence and said, we think that if you measure the internal wave field and plug it into this formula, that will tell you the rate at which energy is moving from large to small scales, and that will tell you the rate, therefore, at which it must be dissipating off the deep end. And they went out and measured with their guests, and they measured it compared to observations of turbulence, and they compared well. And so Greg, over there on the right, who is my PhD advisor, condensed all of this nasty integral stuff into a relatively simple formula, which told you if you measured how much shear was in your internal wave field, which basically tells you the spectral level of it, that is a good way of predicting how much turbulence should be happening at the small scales through all of this wave-wave interaction theory. And so, and then, yes.
So that formula, that's empirical formula, and it's a-
It's a combination. So this is based upon the scalings that come out of the nasty equations on the board. So there was that theory, the one I wrote on the board of these weakly nonlinear wave-wave interactions that was out there in the literature. There was a bunch of other ideas out there in the literature. And so this paper, this paper of Mike's, which I didn't actually put the reference, did I? No. Oh, Greg 89, yeah. Said, okay, I'm gonna make a bunch of measurements of turbulence and I'm gonna compare it to these ideas floating around in the literature. One of them is this wave-wave interaction theory, and then there's another one which has to do with some other things, and decided that the one based upon with the wave-wave interaction theory looked most like the data. And then he just simplified it. Yes,
I guess this theory fits only in open oceans. Or
hold that thought. So people then went and looked in the open ocean, and so you can't see. Here, I'll just unplug and replug.
Sometimes if you step on it, you-
Yeah, I know, but okay. So so this is what people do, is they say, okay, let's say we know that internal waves generally have large, internal tides have relatively large scales and low frequencies. We know something about them, or we can measure them. You plug them into this black box, which is this formula on the board, which tells you that given a certain field of internal waves, they interact in such and such a way, and they steadily transfer energy down to small scales at a certain rate. And that gives you the rate at which energy must be dissipated at the small scales. And so you can do that with a variety of types of measurements. And so Caitlin, who is a student, former student here, said, well, what if we do this well with all the Argo floats? And so, so you take an Argo profile, you could look at the wiggles in n squared. So you can either look at shear, you could look at the wiggles in n squared and say, hey, that's a measurement of how much energy there is in the internal wave field.
And sorry, the Zoom, I think took you out of your share screen.
Oh, okay. Well, yes. Okay. So you can look at, how many wiggles there are. You can say that's a measure of the energy in an internal wave field. You can plug in and say, this is a measurement of the energy in the internal wave field. I know, given a certain amount of energy level in the internal wave field, how quickly waves are doing their nonlinear interaction to transfer energy to smaller scales. And you get an estimate of how much turbulence should result. And so then you repeat 400,000 times. And she makes these maps. And this, I just put for fun, this is a direct lineage from Walter Shipcox to Mike to me to Caitlin. And so it's just like it's an academic to Helen to anyway, so you can make maps then of what you get. And so she took Argo profiles from all over the world and made these maps of how strong she thinks the turbulence is, and compared them to areas where there were microstructure measurements, and they generally look shockingly good. So this is kind of a crazy thing. So the so-called fine scale parameterization of turbulence is something where if you and Charlotte and Ankita have put together a MATLAB workbook that has all of those nasty equations concatenated and or simplified into a form that you can just plug in data that you have, which she will share with you or already has, or
It's on the drive.
It's on the drive.
Show it. Yeah.
But it's based upon this idea. And so before I go into the caveats and how this works or doesn't work in the coastal ocean where you have your data, is there any questions about this magical thinking thought process that leads to this? Yes. Go back.
Go back one slide.
This one?
Oh, yeah, so the single dissipation estimate to repeating many times, is that repeating many times, like, across everything to make the map, or is that like at a given spot to make sure you have a correct estimate?
The first one.
Okay.
Or, I mean, the Argo floats are moving around, so she doesn't have that. But if you had a mooring, you could do this at different times at the mooring, and then you get a time series.
Gotcha.
Yeah.
But it's not a verification.
It is not a verification. No, it's.
And then just confirming, the correction for Coriolis frequency is just because internal waves, they have different frequencies depending on the Coriolis frequency, or is there more to that than?
So there's a Coriolis frequency comes into it because, and the latitude comes into it because the way that waves interact depends in part on their aspect ratio, and like that changes with latitude. Anyway, and the bandwidth changes with latitude between F and N, and so that basically it's because the bandwidth changes with latitude, I guess. And so there's a term that accounts for how wide that bandwidth is. Yeah.
Can you only do this sort of stuff with wiggles in N squared, or can you do it with wiggles in?
Yeah, you can do it with wiggles, and in any way you want to measure internal waves. So there's so you take into your magical black box here. Oh no. Okay. Any sort of measurement of internal waves in the ocean. Actually, I'll go back to Caitlin's figure. So that could be measurements of velocity. That could be, you look at velocity or shear, and that gives you a measurement of how energetic the internal wave field is, or strength. So you're essentially either measuring kinetic energy or potential energy of the internal wave field, either or both. If you use both, then you have a more constrained answer. But
and all of those are called Finescale parameters?
yes, fine scale just means that you're measuring, in this usage, it means that you're measuring something about the internal wave field at scales that are not microscale, so that they're at, tens of meters vertically or something like that, which are easy measurements to make. All shipboard HCPs measure at this scale, regular CTD profiles, Argo floats, moorings. There's a whole ton of data that has measurements at these scales. And you can be like, oh, this gives me an estimate of how energetic the internal wave field is by just, wave my hands and plug it into a formula like this based upon all this crazy assumptions and math on the board. It miraculously, I consider this one of the bizarre miracles of science. Whole bunch of crazy assumptions gives you a crazy formula, which gives you maps like this, which actually look pretty good compared to real turbulence measurements. Just, it's amazing. Yes.
And there is a limitation. I mean, like, do you have a filter to look just the frequencies of the internal waves, or do you use all the field of your measurements?
That's a good question. It makes most sense to just look at the part that you think is from internal waves. But if you then there's a whole bunch of other work that is starting to look at the interaction between internal waves and mesoscale features, which may have similar sorts of resonances or related sorts of resonances, and so it gets a little bit more complicated. But I am gonna run out of time, So I just, so people are also trying to think about how to put this into models, or have thought about it and have done it actually. Which is, so models don't resolve all of the things, like GCMs don't resolve all of these things, but you can take a GCM and say GCMs, you can predict where you think internal waves are generated. You can predict, then you plug in this formula and you can predict the dissipation patterns that you think will result. And so for the open ocean, so one of the, in my previous decade of career, like 10 years ago, my big thing was I led this climate process team that took these ideas and put them into GCMs. And so like the US National Modeling Centers now, NCAR and GFDL, have parameterizations in them, or IPCC class models that are based upon these ideas that give global patterns of turbulence based upon locations of internal wave generation and propagation. But one of the big, I'm not gonna, yeah, okay. So there's a bunch of things that are caveats to this. One, so here's another student, former student Ruth, and her thesis was partly looking at coastally trapped internal tides. And it seems like that might be something that's happening in some of your data as well, that there are coastally trapped internal tides. And those are a super common thing happening near coasts. This is the Mendocino Escarpment, but happening all along our coast. That violates all the assumptions about broad internal waves. Skip this. Murray Levine, who was a professor at OSU and was one of my favorite people in the field until he died of leukemia, wrote a nice paper looking at how you scale the Garrett-Monk spectrum as it moves onto the shelf. Because it's a if anyone is going to Ocean Sciences, he's who our memorial dance party is for at Ocean Sciences every year, this fellow. And so the coastal ocean is different for lots of reasons. And I'm gonna skip this plot by Devin. So I mean, you look at your data, right? And does your data look like a broad band field of weakly nonlinear acting, weakly interacting internal waves at all frequencies? No, not really. Kind of looks like one internal tide coming in and breaking. There are other things happening, but it's not, it violates all of the assumptions that are on the board in the coastal ocean. So something else might be happening. My thesis many moons ago was trying to look at why those assumptions are broken and how we can rescale. If you shorten the water column and make it not broadband, you can get a different version of the scaling, which sometimes works and sometimes doesn't work. I wanted to mention this paper. I think this might be the most relevant series of papers recently for your project. So this was a postdoc at OSU, Johannes, working with data from the Inner Shelf project, which Andrea at least is part of as well. And this is an area, so the idea of this work is that something totally different happens in the coastal ocean. If you want to predict how much turbulence you get from breaking internal tides in the coastal ocean, what happens is you have an internal tide, it's coming in, it's shoaling, so the energy density goes up, and then at some point as it shoals, it gets too big for its britches. And you can measure how it gets too big by either that criteria that was on the board before, that its phase particle speed starts to go faster than its phase speed and it convectively breaks. You can measure it as when its Richards number is order 1, and you guys saw these breaking bores and things, right? So the bores happen for a similar reason when the phase speed, the particle speed starts to be equal to the phase speed. That's when you get funky bores like you saw in the data. So for one reason or another, if you have a shoaling internal wave, as it gets into the coast, it has too much energy to be a linear internal wave. And so Johannes's idea was, he said, okay, what if we know the rate of waves are coming in, they're propagating with their group velocity. We know the stratification and we know how the water is getting shallower. let's just say that the amount of turbulence you expect in a depth average sense is however much turbulence you would need to get back to a state where you're just critical with respect to those parameters. So the waves that comes in, it's like, oh, I'm too nonlinear, I'm starting to break. And so it mixes just enough to return to a state of criticality. So if you combine that criteria with the group velocity, something pops out which has units of dissipation rate, which is the rate at which it needs to slough off energy to stay marginally stable. And so if you make a map, and here's something from his paper, the background color is his map of, I guess this is watts per meter squared, how much depth integrated energy it would need to slough off, propagating and shoaling internal tide to stay marginally stable. And then the dots are places where we had measurements. You can kind of decide if it looks good or not. But I think this is one of the most, I thought, good ideas I had seen in a while. And could be something that would be useful. I mean, he has a formula in the paper that you could just plug into your data like today, and just see if that is telling you something about the rate in which shows internal tide would break. It is 10:30. I think I am done. But there was a lot of maybe too much information for 1 hour, but I will post a whole bunch of references if people are interested in any of that stuff. I can answer any questions there.
Are there any questions on Zoom? Got some claps.
Yeah.
Yeah, I guess you showed that like the stuff with the Argo with the parameterization. Then there are these new ideas about mesoscale interaction, and also this coastal mixing. What other avenues do you think are the big ones for moving forward with this?
Yeah, I think the coastal question of, I mean, patterns of coastal turbulence is totally wide open. Like, it's sort of shocking how little we understand and predict patterns of coastal turbulence. And we know a lot of it is driven by internal wave breaking, but we don't. So coastal one is a big one. Yeah, just what you said, actually. The other big one is interactions with the mesoscale, because the mesoscale also has shear and strain, and waves refract in mesoscale, and they can transfer energy, and there's a lot happening there. Which I think Charlotte maybe talked about a little bit with her course grading stuff.
And are there other scenarios other than like in the coast where your Finescale parameterization would fail?
Yeah, it fails. There's that's Charlotte's. Anyway, I had some slides, but I don't know where they're. It fails where there's strong mesoscale. So in regions of strong shear or really energetic eddies, it does not. It does not do well. It also doesn't. I mean, the other place that a lot of us have been working, including you maybe, is in the upper ocean, like just below the base of the mix layer. Like, there isn't yet time for a broadband, phase, blah, 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 internal wave field to develop. So like, but that's the area just underneath the surface next there for like the 100 meters or so just below there, where all of the heat that is going to be exchanged with the atmosphere or the ice or whatever is actually moves through that zone, the transition layer. And so that area is super important. And this doesn't work there because it just doesn't have a broadband. It's too close to the surface. And so that area is crucially important for a whole bunch of societal things. Or, air sea interaction things, and that it doesn't work there.
I think that is the case with the example I did, because I used upper ocean measurements from the Bay of Bengal, and it doesn't work very well.
Okay,
so
great.
There's an evidence of that in our example.
Yeah, so where it tends to work well is like the deep, somewhere I didn't show the like. I mean, the places it was sort of tested was this section from the Brazil Basin, so deep areas, you know, the eastern half of the Brazil Basin where there's rough topography, we know this is a site of internal tide generation. And the idea here is that internal tides are generated over this rough topography. They start propagating upward. As they propagate upward, they slough off energy through wave-wave interactions to through the rest of the internal wave field, and the rate at which they slough off energy through fine scaly things gives you the rate at which turbulence decays as you go up. And so to get this decay rate right, as you know, the decay rate of turbulence as you go off the bottom in areas of rough topography, it's not one wave breaking. The only way to get this decay scale right is to assume that the wave is sloughing off energy at the rate expected for wave-wave interaction. And so that was kind of like oh my God, it's a real thing. Like that gives you the right decay rate in places like this. So this is an area that's, you know, it's well away from the surface. It's kind of quiet. There aren't a huge, there's a nice paper by Stephanie Waterman, which is the slide I was looking for, but can't find. So she did this in the Southern Ocean and was like, oh man, it's terrible. And the Southern Ocean has a really strong mean flow, right? Which the Brazil Basin does not. And so that sort of led people into thinking, okay, well, you have a really strong mean flow and lots of eddies. That is messing up this quiet, weakly nonlinear picture. So places like the Gulf Stream and places like that probably does not work very well. So that's another answer to Kaiki's question.
In the equator, Kenya always mentions how like extent band of like high that doesn't really like it's not really real. Why was that?
I'm not really sure. I mean, the wave-wave interaction theory gets weird when F goes to 0. But then there's, I think, other things happening there. I mean, that you can figure that out. Yeah.
Any of this
so the nice thing about this theory is that it's agnostic about the details of the turbulence. It says you have if you measure the internal waves are interacting such that they move energy towards dissipation scales. Exactly how that energy dissipates, we don't know, we don't care. But as long as you know the rate at which waves are moving energy to smaller scales, that will give you the average rate of dissipation. You know, people do assume that gives you a rate of energy loss. So you still have to make a mixing efficiency assumption, but.
If there aren't any more questions, we actually have a surprise for you, Jen. It was your birthday yesterday, and we got you some cake. We thought we'd sing you some happy birthday. Sing you a happy birthday. And
Shall we start it off?
shall we? Yeah.
This says a thank you because Jen, for you all to, and we maybe have mentioned before, Jen has been the one really spearheading kind of our project of making, and supporting us through it and, you know, trusting us with very delicate instruments. So we're very grateful, Jen.
Happy birthday, dear Jen. Happy birthday to you.
Okay.
I'm gonna try to slide this cake out now.
Beautiful cake.
It was a Whole Foods cake. We cannot claim any credit for the
Yes.
cake itself. All right, let me see if I can get it out of here. Which is its own drama. Maybe. Yes, we probably should. But I want you guys to see the pretty cake before it turns over. There we go. Aha! That's very pretty. Yay! Of course. Austin, did you grab a knife to cut the cake with? Hey, we have plates and we have forks and things back there, and then we also brought some vegan gluten-free cookies.
Could not find cake. I'm sorry.
No, it's
That's a
okay.
big-
I couldn't, yeah, there was no,
No.
but it's chocolate chip and snickerdoodle. So they're back there as well, if you would like them.
You so.
Cool.
You.
Yes, we could do that.
Yeah.
Those of us who are here.
Yeah.
So would you, yeah, you're welcome to,
Okay.
we got you, president. It is a.
That's amazing. I was considering buying one, but I didn't.
Yeah, so you're perfect. Good. Now you have one. And there should be, I think, a card in there as well. Oh, the card is there. Okay, sweet. And you don't have to read that nowadays. Okay, it's just free. Okay, I will go grab some.
I will stop sharing.
Picture from.
Should we do it?
Oh, yeah, we could get, yeah, a picture with the students, but let me.
Yeah, I can take the photo.
I can, I'm good at Photoshop. I can. So, okay, yeah. You want, okay,
Maybe we could do a selfie.
Yeah, let's do that.
do a big selfie. Well, do you want to get everyone together, do it, or do you just want to?
I don't know.
It seems nicer if everyone's together, I think, as opposed to just a classroom. If everyone wants to come up and do it.
I don't feel like that's a lot of work for.
It, so long?
Yeah.
Alright.
I lost the plot a little.
Yeah, I mean,
Just be the instructor.
Just the instructor.
Thank you.
And I'll.
oh, this is taped on. Okay, I was making sure, but it's, there's a little. Plastic.
Yes.
Yay, and there's a knife. Thank you.
Is there a sonar meeting going on?
No, it's just you and me,
Okay,
so I figured this is our.
we could do, okay, great, we could try.
It's a cake and sonar meeting.
Yeah.
Serious knife.
Those are my only two options. I'm like.
Right, we also actually have a plate.
Wait,
We can take a picture as Jen slices into the.
Okay.
We're taking a photo.
Yeah, oh. Oh, yeah.
yeah. That's
So hot.
It's really hot.
Yeah, I'm sorry. I totally forgot to put some cards in.
We'll put the things out after. Also, it's really funny because when the fans are on, the lazy eye of the owl gets really severe. Jen, would you like to slice the cake? Sure. You don't, too. This is taped on. I don't know why they do.
So.
There's a knife here.
There is that knife. I just don't wanna like. Ruin the structural integrity of this
Oh.
beautiful cake.
Oh, you think it was just
Ankita
all-
bought,
all-
by the way, so thank you, Ankita.
It is very pretty.
It's a lovely cake. I think it's the strawberry shortcake.
It
I
does
did-
look
I
like.
did not think about the plastic structure problem.
Oh, no, you got. So there's the whole thing gonna fall apart then?
No, I think it's just to keep it safe.
Oh, I see. Well, like during transport.
Yeah. If it falls apart now, that's okay. We'll just eat
Yeah.
it.
That's fine.
Okay, yay, the cake is now free of its plastic prison.
I will make a.
I think I have it.
I'll scream, yeah. And you're being recorded now.
We're not being recorded.
We can